Yeah. Where the hell's that? What they do is they say, oh, and then I don't know. I'm saying, you know what I'm saying? Someone else didn't look at the
All right. Hello. So I'll talk a little bit about the midterm again. I'll then do some more memory model stuff. So on Wednesday, we'll have a kind of not exactly new material, but kind of practice for the material from today. In terms of the midterm, so like someone asked, is there an 8 sheet? Because there used to be an 8 sheet in past semesters. Now the thing of it is, the midterm is a little bit earlier than usual this year, and also we're going slightly slower. So we haven't covered what's like usually on the 8 sheet, mostly, which is like str dots, various things. We just haven't done it. And now, what I said when people asked me, like I said, like whatever is like from here that we covered, sure, I'll put it on the 8 sheet if you want. Now, I would say that like the class is really not about memorization. So like if you have like the basic coding math questions, I don't see any reason that you wouldn't have like everything that you need memorized anyway automatically. But just for your peace of mind, sure, like whatever's here that's highlighted is going to be handed out together with the midterm. The goal here is not like, I doubt anyone really ever refers to those things. Well, like some stuff is useful, like whatever, like knowing how .index works exactly, I don't know, stuff like that. But I think it's more for your peace of mind and more so that there's like nothing that you really need to memorize as opposed to understand and practice. The 8 sheet is given as is. It's as if it's something that you found on the internet. I make it policy to never answer questions about the 8 sheet. Like what you get is what you get. On the midterm, like you got to do everything yourself. The midterm itself, so if you don't know, it's on Thursday at 9 hours 10 minutes. It's gonna be 1 hour 45 minutes. Like I think you're used to this by now, if not accepting of it. Yeah. All right, so that's that. And then office hours. So I announced today extra office hours in GB 119 at 6:30. And then tomorrow it's the usual 5:30 at BA 8256. That's just like the usual scheduled office hours on Zoom as well. Yes. It's Yeah. So it's like whatever is the announced office hours. So it's Tuesdays 5:30. So some of you have something at 5:30, some of you don't. So I come in at 5:30 and then I wait until at least like 6:15. If nobody shows up, I leave. If someone shows up, happy to help. And like the idea is it's kind of staggered, right? So like the people who are done on Tuesday at 5 can come in at 5:30, and then I'll hopefully answer their questions like until 6, and then new people come in at 6 who are done at 6. Okay. So the other thing, so I'm sorry that the website is not as up to date as it could be. I'm working really hard on getting it fixed. Right now, I will note that the memory model notes are on here. So that's basically what we started last time and what I'm going to do today, with kind of slight variations and examples, but basically it is what it is. So you can read it if you're more comfortable reading stuff on the page as opposed to listening to lecture, or you could do a combination. Okay. So what I want to do now is I want to go back and talk a little bit about aliasing again. And then we'll talk about shallow copy, deep copy. And finally, we'll talk about calling functions, which we have not done yet. So, okay, so I'll make, just kind of to give you time as well, I'll make a memory table and a variable table. So the memory table would be like this. In the memory table, it's address and then value. And I start, so the addresses, again, are kind of arbitrary. So I usually just start with 1032. So I'll write a little thing to automatically give me the addresses. Why is it complaining? Right, so now I don't have to do it in my head, and I just do it in intervals of 32. So that's going to be like this. And then I also have a variable table. And the variable table has variable or name, I guess, and the address that's associated with it. So when I do something like this, when I say L1 is equal to 5, 6, what happens is I have 5 and 6 in memory first, if they're not already there. Then I put what's on the right-hand side in memory now that I have all the constituent elements. So this would be at 1032, at 1064. And I write at again, just because I want to distinguish between an integer value and the value that happens to be an address. So it's not as if Python stores the, well, it kind of stores the ats, not in exactly this way. It's just a graphical way of saying this 1032, it's not the number, it's an address. All right, even though an address is a number, right? So like 40 St. like Ben is 40 St. George Street, 40 is a number. So, okay, so that's like that. So we've put this this object in memory, and now it's going to go over here. So that's going to be at 1096. And I put the address of this guy. So the address of this is 1096. I put it as L1. All right. So that's putting stuff in memory. So if it's a compound object, first put all the constituents in memory. So make sure that 5 and 6 are in memory, and then create this list where the first element in this case is the address where 5 lives, and this is the address where 6 lives. And then put that, and then we are ready to say that L1 is at 1096. So if we do L2 is equal to L1, what this means is I'm taking the address to which the right-hand side refers, so 1096, and I'm copying it somewhere. So in this case, on the left-hand side, I just have a variable name. So that means that that's just a change to the variable table. So I'm going and I'm saying L2, whatever it used to be, I'm just taking this and copying it over here. That's always what happens when you say something like L2 equals L1. It doesn't matter if it's L, right? So like if you say something like A is equal to B, that's exactly the same always. You're taking the address that corresponds to B and you're copying it to the address that would correspond to it. All right. But that means that L1 and L2 are aliases. So that means that L1 at 0 equals to, let's say 6, also makes L2 at 0 equal to 6. And like, of course, you're going to the list that lives at address 1096, and you're saying this is now something new. Well, like, of course, like whether you access it via L1 at 0 or L2 at 0, it's going to be 6. So this is like this. All right. So we can represent it graphically as well. So the way you would represent it graphically is you would say, okay, so L1 is initially 5, 6. Extra bracket here. So then I'm making L2, and L2 is not its own separate list. It's that L2 is also this. Right? So yeah, like I change, like really it's kind of like this. So I change this 5, well, L2 is also this list. I never created a copy of this list. On the screen, it's that the only list that I have is this guy. So I change this list, well, yeah, everything changes. All right. So I'll repeat this point several times, but this is not something so aliasing is not a phenomenon that's unique to lists. So if you say something like A is equal to 5, well, now A is this, and we copy this address over here. That's exciting. Okay, nice ringtone. Sorry. So if I say B is equal to A, what happens? Well, same thing. This gets copied to over here. A and B are aliases. The thing is, it's not an interesting fact that they are aliases, because unlike with lists, there is no equivalent to going A at 0 equals something new. There's no like go and change the first digit of A to something new. That's just not available. So what is available is saying A is equal to 6 now. Well, A is equal to 6 means take the address of this, so 1064, and copy it over here. Well, now A and B are not aliases. It works the same way with lists. So if you say L2 is something new, some other list, yeah, like you change the variable table, and L1 and L2 are not aliases anymore. Yeah. Did I mess it up? So I said B equals A. Sorry, so it seems correct. So here, like A was 5, B is this. Oh, yeah. So A is 1064. Yeah. Yeah. Was that a question? Yeah.
So, the reason that people worry about this knowledge is this we have this ability to square out and everything.
That's exactly right. Yeah. Yes.
Is the numbers that always stored in that address, or is it
It's a little bit annoying because 6 actually is always stored at the same address. 6,000 is not, but 6,000 is annoying to type. So for now, just imagine that 6 is already pre-stored, which it happens that it is. Yeah.
Does it have to integers, like variables beside the integers are aliases, since integers are.
Well, exactly. So it doesn't. Right. Yeah.
When you assign like access in the memory table, that actually already exists.
Well, the address is a physical thing. It's a location on the chip. So in that sense, it exists. But in general, so kind of if we look at the memory table, it's that some of the memory table is used up for stuff, some is not. So really, if you actually look at the values in each cell in the memory table, it already has some value. Like there is no empty, right? It's a pattern of zeros and ones. It's just that some of it is empty in the sense that we are able to overwrite it to write stuff that we actually use. Some of it is used, so we're not allowed to change it. Yeah. Yes. So if you remember, you can ask for the so you can ask for example, a D of A. Well, A is not defined. So you can ask for a D of A, and that's going to tell you where A refers to. So there is not kind of a universal way that would work to query like every possible cell, but for every variable, you can check what it refers to. In terms of the memory table, in terms of the variables table, yes. So we haven't done it, but you can do globals, and that's going to give you all the global variables that are defined. And then you can go ID for each of, so it's just that like an Anaconda, like some of the variables are the previous commands. So that's why it's kind of dirty. But if you go to just Python 10, oh, that's okay. I need to turn off my IPython, but that's like a little bit cleaner. So you have like all this stuff, but yeah, okay. So let me just show you briefly. So globals now is going to be, well, still some stuff, but not as many. And then you define like x equals 5, and now the X is in the globals as well, in addition to all the other garbage. It's somewhere there. Oh, it's like actually the last one. Yeah.
Functions stored in the memory table.
Yeah. Functions are also variables. So yeah. So okay. So this is like this. So I'm gonna so now let's say that you have two lists. So I'll reassign stuff. So let's say that you have, this is 5, 6, and then this is like 6, 5 or something. So here L1 is going to be at 1032. So A and B I'm going to remove. So here 5, 6. So this is going to be 1032, 1064. And then this is going to be the other way. And then this is like this. So this is 1096. And this is 1128. And then what you do is L3 is equal to L1, L2. So that's the same kind of thing that you saw in the lab last time, right? Where you have a list of lists as a variable. Okay. So how would you handle it in terms of the memory table? Well, you take the right-hand side, and the first thing is you put it in memory. So here you would say, well, L1 is what? Just copy this, so 1096. And L2 is 1160. All right. So now, if you wanted to, for example, get at this 6, what would you do? Well, you would say L3 at 1 at 0. So L3 at 1 is this list, and L3 at 1 at 0 is this 6. Right? So that's what you did with tic-tac-toe last time. Let me check. Is Discord saying anything? Nope. All right. So that's like this. So now what happens if I say L4 is equal to L3? By the way, I forgot to put an L3 here. So L3 is going to be at 1160. So when you say L4 equals to L3, well, again, kind of what's on the left-hand side is just a variable. So you just copy whatever this is to here. So you copy this to here. So the rule is if on the left-hand side, it's not an element of a list, you don't go into memory table. It's just a manipulation on the variable table. Right? So you copy this to here. So this means that L3 and L4 are aliases. Right? So that means that L3 at 0, changing L3 at 0 is the same as changing L4 at 0. And changing L3 at 0 is the same as changing L4 at 0, and so on. Make sense? Of course, because like L3 and L4 are the same list. So like you go inside 1160. Well, at this point, it doesn't matter where you got to 1160, like to here or to here, via L3 or L4, it's all the same thing. So like maybe you change this guy, or maybe you say, oh, I need to go to 1096 and then I need to change this guy. It doesn't matter where you started in your code by referring to L3 or L4, you'll end up in the same place. Right? So now I want to start thinking about, okay, how do I disentangle those things? Like right now, L3 and L4 are completely entangled. So in order to think about it, I'll first think about how do I disentangle just this kind of stuff. So I'll copy this to a new page and we'll come back. So let's say that we're just here. So that's not in memory. So now I'll say L1 is equal to L2. What happens? Same thing, right? So L1 used to be this, and now we're just gonna copy this to over here. So L1 and L2 will become aliases. So again, changing L1 at 0. It's the same as changing L2 at 0. All right. So how do I make it so that it's not like that? Well, there is a way, which is I can say L1 is L2.copy. So L2.copy, so that's something we've done last time as well, actually programmatically. So this is like the library function to do that. So this is saying take L2, which is at this point is the same as L1 anyhow. So 1128, take L2 and then make a copy, have it live somewhere, maybe here. Why is this? Yeah, so maybe here. So now we have a copy like this. And then copy the address of the new thing that we just made. So 1160 in this case to L1. All right. So now changing L1 at 0 means changing L1 at 0 is like the stuff at 1160. Why is it 63? $64, sorry. Okay, that's not supposed to be like. Okay, that doesn't matter. So this is, oh yeah, this is fine. So changing the contents at 1160. Changing L2 at 0 is changing the contents at 1128. So those are different. Like you change this versus you change this, those are separate. Right? So in terms of the picture, L1 is 66, and then you're saying L2 is also 66. But changing this is not the same as changing this. Okay. Now in track, yeah.
You just do L2.copy and that just makes a list of L2 or
Well, it makes a copy of L2 if you don't assign it to anything. So if then you like what this does is it computes this guy, right? But if you don't save the address 1160, then which is what you're doing here by assigning to L1, then you can't access it. Yeah.
Just when you do L2 copy instead of just doing L1, L2, it allows you to create like new entry in the memory.
Well, so entry, I'm using entry for something else. So what it does is it takes L2. So L2 was 1128, this guy, and it copies it somewhere else in memory. Right? And then what I can do is I can change the original thing, or I can change the new thing now. And those are, well, I mean, they're not, so everything is separate if it's not the same thing, right? So like it was that L1 and L2 were literally the same list. Now I made it so that they're different lists which happen to be equal.
Right.
All right. So in terms of the picture, it's going to look like this. And of course, like I go and change this to something else, you know, L2 doesn't care. So to come back to how we did it last time, this is the same as saying, so I'll name it shallow copy for reasons that are going to be clear in a second. So shallow copy, I'll say is initially empty, and then I'll say for E in L2, I'll say shallow copy append. So that's the same, right? So what I'm doing is I'm going through every element of L2 and I'm appending that element to shallow copy. So crucially, I'm not creating a copy of E. I'm just saying it's also going to have this. So basically, I'm copying this address over here. So I'm copying 1064 over here, and I'm copying 1064 over here. So that creates a problem when the situation is more like this. So I'll copy the variable table and the memory table so I don't have to recreate them. So let's say that I have my original situation, right? So I have L1 is 5, 6, and I have L2 is 6, 5, and I have L3 is L1, L2. So here, again, I need to create 5, 6. So at 1032, at 1064. And then at 1064, at 1032. And then L3 is L1, L2. So this is at 1096, at 1128. So L1 was 1096. And L2 is at 1128. And L3 is 1160. Right? And now let's say that I make a shallow copy of L3. So I'll say L4 is L3.copy. So that's called a shallow copy. You'll see in a second why. So what happens now? Well, we create a copy of L3. So that means we literally take this. So this is the L3. And we copy and paste it. And then we're saying, okay, so that's L4. Well, if I now go to L4 at 0 at 1, what is this? Well, L4 at 0 is at 1096. L4 at 0 at 1 is this guy. So let's say that I say that this is 5. Well, that means that I go here and I copy this to over here. And then, like, of course, like this is L4 at 0, but this is also L3 at 0. right? So so this one may be clearer in the diagram. So what are we doing? So we're saying L1 is 5 fixed. And then L2 is 6 5. And then L3 is L1 and L2. So that's like that. And then L4, I'm not sure I'm going to capture. Yeah. So then L4 is also this, right? So L3 and L4 are the same, have the same contents, but they're separate lists. But that's also going to go here. And this is also going to go here. Right? So L3 and L4 are two separate lists. But L3 at 0 and L4 at 0 are both just this guy, are both just the 5 6. Does that make sense? So I go in and I change this 5 6 to something else. So in particular, I change the 6 to a 5. Well, L3 at 0 at 1 and L4 at 0 at 1, they're both the same thing, so they're both going to be affected. On the other hand, L1 and L3 and L4 are separate lists. So if you say L4 at 0 is equal to 6, well, L4 is 1192. So L4 at 0 is this guy. So you're saying instead of being 1096, it's now just going to be this one. So just copy it here. Well, L3 is not affected. So in the picture, this would be kind of like we're saying L4 at 0 used to be L1. So we're just canceling this. And instead, we're saying that this is now 6. Make sense? So there's multiple ways of thinking about this kind of stuff, and I see different people kind of, well, some successfully, some not, but different people using different strategies in order to understand this. So some people just write out the memory table and just follow the rules. So the rules, whatever we did last time, are quite simple, right? So if on the left-hand side you have a variable, well, just copy the appropriate address to the variable table. Always. If on the left-hand side you have an element, well, go in the memory table and change that element. On the right-hand side, if you are creating a new object, put it in memory, copy the address. If you have an existing object, just copy the address of that object to the left-hand side. That's pretty much it. If you just follow those rules, you'll figure out what's happening. At the same time, it's not easy to do this. It's like the rules are simple, but applying them can be pretty hard. So I think the diagrams are more intuitive. The downside of thinking in terms of the diagrams is it's harder to formalize the exact rules of how the diagrams work. So if you kind of feel that you definitely understand the vibes behind the diagram, you can do that, but you should figure out whether you trust yourself on that, right? So if you're able to reliably predict and then try it in Python and whatever you do on the diagram works, well, probably you got it, so you can do the diagram. If not, go back to thinking about the memory tables because that's really what's going on. once you've gotten kind of, I think it's probably like, for most people, it's like a year or two, in order to really internalize it, so that you can do it in your head. Well, once you reliably can predict what's happening in your head, don't just say, I think I can reliably do it, just check whether it's actually true by running some code. But at some point, like, I don't either draw diagram, well, like for like complicated stuff, I draw diagrams. But usually I just kind of can do it like almost in my head. But that's just because I had like a lot of experience. So the most usual thing in which people don't succeed is they just kind of say, oh, I'll just do it in my head, without first testing that they can reliably predict just in their head what's going to happen. So don't do that. So I think kind of most people who are successful in the beginning are the people who are doing the memory tables. Yes.
In line 6, shouldn't it be not instead of now?
In line 6. Is not affected. Yes. Yeah.
When you do L4 equals L3 copy, why doesn't it create a copy of the lists within L3 as well?
Well, because that's what .copy does, is it creates a shallow copy. So why